พี่น้องลูกหลานพี่ป้าน้าอาปู่ย่าตายายทุกท่านนะครับครับขอต้อนรับสู่งาน Public Talk นะครับโดยหัวข้อการผจญภัยของ Satlantis นะครับดาวเทียมขนาดเล็กที่ปฏิวัติการสำรวจโลกและเอกภพโดยศาสตราจารย์ Rafael Guzmán นะครับ So welcome all ladies and gentlemen, and we would like to invite you to the public talk by Narrated in the topic of new frontiers of in-Earth observation and the exploration of the universe, the adventure of Satlantis by Professor Rafael Guzmán. And without further ado, please give a big hand to Professor Rafael Guzmán.
Thank you. So thank you all, actually, and good evening. It is a real pleasure to be with you today, and I do apologize, I cannot speak Thai, but I promise the next time that I come and visit you, I hope that I can at least say a few words, actually, in your language. It's been a very interesting day visiting Narit, and it is indeed an honor to be able to share with you what it has been the adventure of creating Satlantis, which is a company dedicated to launching cameras and satellites into space for both Earth observations and for the exploration of the universe. So if I have to start, I have to go back to 2010. And at that time, I was the chair of the astronomy department at the University of Florida. And University of Florida is a partner in the Gran Telescopio Canarias. This beautiful facility that you can see here is in the Canary Islands off the shore of Africa. And this is the largest telescope in the world. And you can see the size, comparing the people to the actual size of the telescope. It's a beautiful facility. And we were celebrating the inauguration of the observatory. And at that point, I met the director of the Spanish Space Agency. And Spain had launched 2 small satellites, like these ones. You can see tiny, particularly compared to the size of the big telescope before. So they have launched the 2 satellites, but they had not included any instruments inside. But we at the University of Florida, we have built very large instruments like this one for some of the best observatories on Earth. So I thought that we could actually start developing small instruments for the small satellites, since Florida is the state in which much of the space race took place. So we had this idea, but we needed to come up with a project, with a scientific project. And I have been very interested in learning about dark matter in the universe. And I don't know how many of you know what dark matter is. Do you know what it is? Of course you don't, because nobody knows. If you knew, you would be the next Nobel Prize. So just imagine for a minute that you are an alien species. You are extraterrestrial. And you can only look at the Earth during nighttime. And you're trying to see what is the distribution of the continents based on the lights that you can see at nighttime. And this is very much the image of the Earth at night. Right? You can only see the lights of the cities. So if you try to reconstruct the continents based on the distribution of lights, you can see that Europe will be very well approximated by the distribution of lights. Part of North America would be, and of course part of Southeast Asia, including Thailand and India, but you would be missing most of Africa, most of Siberia, large chunks of the Earth. So a similar question arises in the universe, whether indeed everything that we can see, all the stars in the night, all the galaxies that we can see with our telescopes, is indeed everything there is, or instead there's much more that we cannot see. And in fact, according to the observations and the models that we have made about the universe, it turns out that it is very likely that what we see, all the galaxies, sit on a much larger distribution of matter that we don't know what it is. It's dark, it does not interact with light, and that it may account for the majority of the content of the universe. But we don't know what it is. So we know that it is there because according to the observations and the models, you have, in this case, this model of the formation of a galaxy like the Milky Way, this beautiful spiral galaxy where the Earth is located at. And you can see that in order to create such a galaxy, according to our models and our observations, you need to bring a lot of gas from the surrounding areas that eventually will collapse to create this spiral galaxy in the very center. And the same model that reproduces how galaxies form reproduces the distribution of all the matter in the universe in this filamentary structure that looks very much like the neurons in our brain. So the models and the observations do a very good job in explaining most of the observations except at one scale in the universe, which is the scale of the single galaxies. And so what you see here is a galaxy surrounded by a halo with very small galaxies like the Magellanic Clouds. We call them satellite galaxies, right? And the same model that predicts beautifully the properties of the universe fails to predict how many satellite galaxies are around galaxies like the Milky Way today. In fact, they overpredict the number of these small, tiny objects around the big galaxy in the center. They predict many, many more, hundreds of satellite galaxies, more than what we can observe. And if in the end there's a disagreement between theory and observations, we will need to change the theory. But this is a huge step because the theory can explain most of the other properties that we can see in the universe. So it turns out that to do these observations that you can see here in the modeling, this is simply the fact that some of these small satellites may have actually been destroyed as a result of the interaction with the galaxy in the very center. So what it was started being a tiny little satellite, after orbiting a few times around the galaxy in the very center, this big red object in the center, it gets stretched out. All the stars will be stretched around the original orbit of this satellite galaxy. And these are what we call stellar streams. So maybe it happens that some of the satellites that we could not see is because they are not there anymore. They have been destroyed and they will leave these streams afterwards. And we see some of those streams, and this is what you can see here in dark, right? But these are the features of the stellar streams, these orbits around galaxies in the center, very much like the Milky Way, right? But the ones that we see are not enough to explain the difference between the predictions and the observations. And it turns out that you can do this much better if you have a small camera like this one that we call ISIM, and we developed at the University of Florida. ISIM stands for the Integrated Standard Imager for Microsatellites, for the small satellites. It could be on board this satellite, which is the size of a small washing machine, about this big. And we can launch the satellite from the Kennedy Space Center in Florida in an orbit like this one, in which you have the camera always, this is the sun over here, and you have the satellite orbiting in this orbit around the Earth and always looking in the opposite direction to the sun towards the universe. And this was the original idea. We thought that we had the camera, we had the satellite, we had the place to launch it from the Kennedy Space Center. We just needed the money. So this is the first agreement between Spain and Florida to be able to launch this mission that we call DOOMS. But as I said, we didn't have the money, and it just happened that a few months later, the Spanish Minister of Science and Innovation came to visit the Kennedy Space Center to view a launch of a Spanish satellite. But the launch was delayed by one day, So she came to the university to visit. And so I was explaining to her what we were doing in collaboration with Spain, and then she asked the famous question. This is very interesting, Rafael, but have you considered, instead of looking out into the universe, looking down to Earth, and whether you think that this technology will be particularly good at observing the Earth? And I said, no, I'm an astronomer, and was thinking always looking outside, but let me do some tests, and I will answer your question. So we actually took some of the best Earth observation images taken from this satellite, GeoEye. It's $800 million, right? It's a big satellite, the size of a bus. And it produces beautiful images. You can see even the cars in the highways, right? So we simulated how such image could be seen with our small camera and with new techniques for processing the data. And this is what we came up with. So you can see that it's slightly blurred compared to the big one, right, to the big satellite, but it's quite good. And particularly taking into account the size. See, this is the original satellite, and this is the new satellite, much, much smaller, and therefore much, much less expensive, about 100 times less expensive than the big satellite, which means that we can launch several of these satellites, and every of these satellites in this low Earth orbit will go around the Earth once in 90 minutes. So every 90 minutes, it goes around the Earth at about 20,000 kilometers an hour, which means that if you have several of these satellites, then you can obtain images almost anywhere on Earth just every 30, 45 minutes. So you have access to real data from space, which is very difficult to do from just having one single satellite. So we thought that this was a really good idea, and therefore we signed the second agreement between Florida and Spain, this time at the highest level. And you can see here the Minister of Science and Innovation in Spain, and over here you can see the Lieutenant Governor of Florida. And they promised that they would give us the money to be able to launch the mission. But soon after signing this agreement, there were elections in the state. There was a change of government, and the new government was not interested in pursuing the satellites. So we were left with a good idea, and again, no money. So a year later, this is now 2012, I was visiting Barcelona. And in Barcelona, this beautiful city, I don't know whether some of you have been there in the Mediterranean, it was a very wealthy city at the time because of the football team that they have, the Barça. And the mayor of Barcelona was very interested in having access to images from space so that you could have direct information that the citizens of Barcelona could have in their cell phones, right? So they liked our idea of launching this small satellite and tell some information about the life in the city, how hot some of the areas in the city were, what was the traffic, what was the contamination in the different streets, whether there was a parking spot or not. We could actually do all that from space. So we decided to propose building a center between Florida and Barcelona that we call Sensat, to fabricate and launch small satellites, both for astrophysics and for Earth observations. And we signed the third agreement between the city of Barcelona, you have the mayor here, the presidents of the major universities in Barcelona, and the vice president of the University of Florida. And guess what? Soon after that, there were elections, and there was a change in government, and the new government in Barcelona was not interested in satellites. So we were left with no money. Very good idea, no money. In the meantime, we were trying to test the camera. Remember this small camera that I showed you earlier. And these are the first prototype. Instead of being a binocular camera, this was just a single telescope. And we were trying to test whether it could actually withstand the very low temperatures in the upper part of the, well, beyond the atmosphere of the Earth, right? And it's vacuum. There's almost nothing right there. So when we have to put it in a special chamber that simulates the vacuum conditions and the change of temperature between the daytime of the orbit and the nighttime of the orbit. And we failed because the coating of the lenses started peeling off. So we have to go back to the drawing board and come up with a second version of the camera. This is the second version, now a binocular. And we actually put it back in the vacuum chamber. And this time, this one actually was all right, but we failed the second test, which is the vibration of the camera. Because remember that the camera has to be on top of a rocket in order to go all the way to low Earth orbit. And it has a lot of shaking to do while it goes all the way to the orbit. So the whole camera was destroyed during this test. And it was disheartening because now we had no money, but we have no camera either. So at that point, I could have said, okay, enough, we tried, and in the end, it wasn't meant to be. Instead, what I did is to use an untapped part of funds, which is my own lifetime savings, and decided to start a new company, Satlantis. And I decided to do that because I was convinced that the idea was really good. And particularly when applying the camera to looking down on Earth, there were three major advantages of our camera. One is what we call the super resolution, is the ability to see very, very small detail right on the Earth. And typically, the larger the camera, the smaller the detail that you can see. But our camera was very small. It's about this big. However, because of our technology, we were able to see cars, for example. Not humans, but cars. It's about 2 meters. So we also have the multispectrality, meaning that we can get color images, but it doesn't matter how many colors we have in our camera, we don't degrade the spatial resolution. While the traditional cameras, they do. If they have 3 colors, their spatial resolution is degraded by a factor of 3. Ours, no. And the final one is agility. And agility means that we could actually observe the Earth not at a fixed angle when the satellite moves in its orbit, but we could actually change the position of the camera while the satellite moves in its orbit. And this is something that other cameras couldn't do because it will blur the image. So because of this, we decided to go back now with my savings, and of course, the company was in my garage, as every startup company. And then we came up with a third version of the camera. And this one you can see, this is the binocular, both in the vacuum chamber and on the vibration table. And this time we passed vibration and we passed the thermal vacuum chamber tests. And after we do this, things started to look much better. So we were able to close the first investment round for the company, and we got the first funding from the European Union to launch the camera. Because in the space, you are nobody till you actually can test your camera in space. And for us, the key test was with the International Space Station. And this is the camera, now in the space shape. Here you can see the binocular. It is covered with this special film to protect it. And we decided to launch it. And I'm going to give you the video of the launch from Tanegashima in Japan. It was one of the most emotional days, actually, of my career. And I will let you watch.
Engine start. Activating the thermal batteries. Go.
Main engine started.
And we have liftoff.
A rising sun over the land of the rising sun as JAXA's H-2B rocket and the H-2B-9 cargo craft take flight.
That is a very nice sentence, the rising sun over the land of the rising sun.
Roll, pitch, and yaw program in effect. The H-2B rocket takes flight to the International Space Station.
So it went actually to leave this cargo, which is the H-2B-9, and inside the cargo was our camera, as well as many other equipment for the astronauts in the International Space Station. And it took 2 days for the cargo to come at the same speed at the International Space Station, and then for the astronauts to grab the cargo with the arm, the deployable arm, that you can see here. It's extremely delicate maneuver. And now they capture the cargo space and they're going to bring it to the International Space Station so that they can then bring all the equipment inside the station. They have to align it very precisely just to make sure that there's no possibility of a collision, that it would be, of course, catastrophic at 20,000 kilometers an hour, remember. That was for us the beginning of testing our camera. And the most important thing that we have, the people. This is the team that actually launched the camera to the ISS. And we were extremely happy celebrating actually that the first stage was done. Now the camera is on the International Space Station. But this was just the beginning, because now you have to bring it inside the space station. And this is what you can see here with the commander, Chris Cassidy. And this is our camera behind. It goes through an airlock, and then with this second arm, then you deploy the camera, it is right there, into the Japanese outside platform called Kibo, looking down on Earth. And only then we can start taking images of the Earth. So this was done, and this is among the very first images that we got. It's in black and white. We didn't have color in the first version of the camera. And over here you can see an area near San Diego in the United States with an airport over here. And here you can see the San Francisco and Berkeley views of the Bay Area, also in the United States. Now, if you zoom in on the airport, you can see that with this tiny little camera, remember, it's about this big. Right. So it's moving at 20,000 kilometers an hour. However, you can get these beautiful images. You can actually resolve the lines in the runway. You can also see how many blades you have in the helicopters, or how many engines you have in the airplane. And that was a major achievement. So we were able to demonstrate super resolution, the first of the 3 key innovations. After this one, we decided to send another one, and in this case with a color information, right? And you can see the filters here, the green and blue and red and infrared filters in the 2 different channels of the binocular camera. Also, we wanted to test agility, and that's why we mounted the camera on top of this gimbal so that it would move perpendicular to the orbital direction of the International Space Station. So this second camera was launched at the end of 2021, also from Kennedy Space Center. And here you can see now the camera being positioned in the outside part of the Columbus platform, which is the United States platform, also looking down on Earth. And you can see the first images. We were completely taken aback by the beauty of these images. This is now a much smaller camera. It's only 7 centimeters, like this, wide. However, see the amount of detail that you can see with these beautiful color images. This is the, well, do you know what this is? It's difficult just with this information. There are a lot of boats, and it's a narrow channel. This is the Suez Canal. And all the boats that are waiting to go inside, but once that you do zoom, you can see all the different construction of the different facilities and the industrial area at both sides of the canal. This is one image. This is another one. At the time was also the World Cup, the football matches in Qatar. And this is an image of Qatar. And if you do zoom in, you can see one of the stadiums over there. Another beautiful image. This is now in China. And what you can see here is the typical color image that we can see with our eyes, as compared to the same image when you bring the near-infrared data. And the first thing that you notice is how red the vegetation is. It looks green to us because our eyes can only see in a certain wavelength of light. But if our eyes could actually see in the near-infrared, everything around us that we see green, it will look extremely red. And that's part of what you can see here in the near-infrared. And you can see also some of the sediments in the water coming from the river here. And even a better view of the difference between the amount of vegetation in green with our eyes and how red it is when you look at it is associated to this image. Again, the same location, two different colors. And this is the coastline in Australia. And what you can see is the contamination by the red algae. And you can see it extremely red in the near-infrared, right? See how red the ocean is in this location, as well as the river mouths in the coastline. These are just simply examples of the beautiful images that we got with such a very, very small camera. Now, we were able to demonstrate the three key innovations of the camera. Therefore, we were ready to go one step further, not just to launch the camera to the International Space Station, but to actually launch an entire satellite. And because the camera is very small, the satellite is also very small. It's a little bit larger than the satellite that I saw here in Narit that some of the engineers and students are building. This is the satellite. It's only 30 centimeters, well, sorry, this is 40 centimeters high and about 20 by 20 centimeters wide. And the camera goes right there. Again, it's a small binocular camera. And we launched this satellite from the Kennedy Space Center using SpaceX. And you can see here the moment that in May last year we launched it with big celebrations of the team all across the 4 corners in the world. And let me show you also the video of the launch, because there's some really nice features that I wanted to share with you.
4, 3, 2, 1, 0. Ignition and liftoff. The 1D chamber pressure is nominal. Vehicles reaching downrange.
This time we were able to view in person the launch. The pandemic was over, and it is truly impressive to be able to see this in real life. The first thing that takes your attention is, of course, the huge burst of light with ignition. But the second thing is that after the burst of light, the sonic boom actually comes. They're just celebrating the separation of the first stage of the rocket, and this first stage that is now off will actually come back to Earth, as you will see in a minute. So as I was saying, after the burst of light, what you have is the sonic boom, and it is so loud that you cannot hear anything else, and you feel it right in your chest. It is quite an experience if you have the opportunity to view a launch of a rocket like this one. So I'm just going to move quickly.
We can see deployment of the grid fins there on the first stage. On the left-hand side.
So that I can show you now, the first stage that you saw that separated before is now coming back to Earth.
Just
this
after
is
landing,
one of
our
the
59
coolest things that I've
spacecraft
seen
will
lately
not separate from the
in
vehicle, will
in
activate, and you
rocketry.
should hear that call out over the
So
net.
it's coming down
Let's listen in for these
and it's going to
activities
land
happening
in this
quick
area,
sequential order.
simply maneuvering with these pieces, and you can see that it's coming back.
And back shutdown.
And a perfect landing. This used to be something that we watch in the movies. Now it's a reality. And what you see now is the ejection of our satellite. There it goes. That was already in orbit, and that was our satellite. So soon after this, everything worked well. I cannot show you the images because we sold the satellite immediately to a country, and now they own the images. But everything turned out to be fantastic. So after this success, we were able to close the second investment round, and our investors are now gas companies in Spain, like Enagas, or in the United States, like Williams, because they're very, very keen on detecting methane leaks from their oil and gas facilities. And of course, the methane is one of the worst greenhouse gases because it tends to retain a lot of the heat, and therefore it contributes a lot to the global warming. And the oil and gas facilities, the oil and gas industry really wanted to monitor how much of the methane is being leaked into the atmosphere. So we thought with the same camera of a way to be able to detect methane from low Earth orbit, and we call that JSAT. And this satellite will be launched now in June, this time from California. And the way that the satellite works and why it is such a competitive advantage is, remember that we have access to agility. So this is the orbit of the satellite. This is the pipeline from Williams. This is Florida. And our satellite can actually follow the track of the pipeline while it is moving in its orbit. And again, this is something that no other satellite can do at this moment. We were able to demonstrate that we can actually see methane here in color from some of the chimneys of the facilities in Spain. So we're looking forward actually to demonstrating now fully the capability with a new launch in June. And we're also talking to the Thai government because PTT, the main gas company here in Thailand, is also interested in monitoring the methane leaks. And this is some of the simulations that we, that we made for the Thai government, as we can actually follow the track of the pipelines that PTT has in the southern part of Thailand. Now with this, now we have grown Satlantis to be about 100 people in two places. In Gainesville in Florida, this is the incubator of the University of Florida where everything started, and the main headquarters that are now in the north of Spain. And the facilities are beautiful, and the technology is really nice. We're very proud of it. But I have to tell you that the most important thing that we have is the people, is the team. It's a very young team of engineers and scientists, and their drive, their ideas, their passion is what really is making possible the success of Satlantis. And you may ask, okay, Rafael, what happened then to your original idea of using this technology for the astrophysics mission to explore the nature of dark matter? So last year, we came back to the original goal to be able to study the universe. And we submitted two proposals, one to NASA, called DOOMS, the original one, and unfortunately, we did not get it. But we were not discouraged, and we decided to submit another proposal about the same scientific goal, this time to the European Space Agency, that we called Arrakis, so DOOMS and Arrakis. And this time, we got it. And we got it, and this is in collaboration with several European nations, where Thailand is also participating thanks to Dr. Chancheurai and the NARIT, the National Research Institute and the Observatory. So we're extremely happy, actually, to start this new mission. It's a huge mission that will last for about 10 years finally we will be able to carry out our dream, which is to explore the nature of dark matter in the universe. And just to let you know that we started actually in January working at the headquarters of the European Space Agency in Holland. It was extremely demanding. We were sitting in this room with another 25, 30 engineers from the European Space Agency, just discussing every single aspect of our mission. So I hope that in the near future, if I can come back again, I can tell you about the progress in our mission and how we're doing trying to realize the dream of understanding what the nature of dark matter is. So before I finish, I just wanted to say a couple of things that I've learned on my personal experience to this. So the first one is that if something is not worth doing, do not spend too much time on it. But if you are convinced that something is indeed worth doing, you believe on it, just keep working on it, because tenacity is the big difference sometimes between being successful or not being able to reach there. The second thing that I also wanted to say is that we shouldn't be afraid of failing. I mean, we should avoid failure, but we should not be afraid that sometimes we fail. Because if we don't fail, it's because we have not attempted anything new ever. So if you want to be innovative, you want to be creative, don't be afraid to fail, learn from the failures, and continue actually pursuing your dream. And with this I finish, and I want to thank you very much actually for your attention this evening, and it is a pleasure actually to take any questions that you may have. Thank you.
So anyone has any questions มีคำถามไหมครับภาษาไทยก็ได้นะครับเดี๋ยวจะแปลให้
You can ask me how can you get a ticket to come and view the launch of the next satellite in the Kennedy Space Center. Talk to me afterwards. Yeah. But if you can, it would be a fantastic experience, I have to say. Yeah.
ระหว่างรอคิดคำถามนะครับเดี๋ยวสตาฟครับขอใบลงชื่อด้วยครับระหว่างนี้ถ้าใครมีคำถามยกมือได้เลยนะครับ If anyone has any questions at all please raise your hand it could be in English and Thai
If I have taken a picture of? Yes. And I need some permission to show it, but it really, really is beautiful. Because the coastline and the vegetation, it comes beautifully. So if I get the permission, I would love actually to share with you. Yeah. That is a very good question. Let me see, 1,250,000, no, 2,300,000. I lost count. Maybe 3-4 million images, and this is just in 1 year. So it's really, really, I mean, you create a lot of data because you're getting a snapshot as the satellite goes. And remember, the satellite goes around the Earth every 90 minutes. 1 hour and a half, and you have gone around the Earth, and then again. By the time that you go again, the Earth has moved a little bit because of the rotation of the Earth. So you see a different part of the Earth's surface. And like this, about 14 times a day, 365 days a year, for about 5 years. So it's a lot of data. Yes.
มีคำถามไหมครับ
Yes. Sorry, I couldn't hear you very well. Sorry about that.
Tornado or earthquake, and And if these images will be helpful, like can the governments contact the companies and
Yes, so the main goal right now has been to use the images for agricultural purposes. And in Florida in particular, really bad disease, which is called citrus canker. And you know that Florida has plenty of orange trees. Well, they are dying. About 80% of the orange groves are dying because of this disease. So they would like to see images from above because you can cover the entire state of Florida so that you can distinguish which tree is sick and which tree is healthy, and being able to take any preventive measures before you spread out the disease to all the healthy trees. And for that you need resolution, about 1 meter, which is exactly what we are providing. And you also need color, particularly in the near infrared, because the vegetation is very sensitive to either sickness or the lack of water, and you can actually see that from the near infrared and the visible colors. The second thing, for example, is the coastline. And Florida also has quite a long coastline, as Thailand has. And this is mainly for red algae contamination that affects also tourism. And also it could be for illegal fishing. So those are the main applications. The new one that we're going to launch, in addition to that, can also see methane leaks, and that's why it is important for the oil and gas industry. The images are available, and if there are any agencies, research centers, or government agencies, of course, they can contact us. And even more, if they were interested in having their own satellite, what we are doing is to partner with research centers in these countries so that we can develop jointly the satellite to launch it and to operate it from the country itself. Yes.
Any more questions มีคำถามไหมครับ
Oh, yes, over there.
Which part of satellite you will develop it first?
Yes, so the first one was the camera. That is our heart, right? And heart and brain. After the camera, because the camera, it's very powerful, but also has the drawback that generates a lot of data. So every 0.1 milliseconds is taking an image of the Earth. So imagine taking images every 0.1 milliseconds. So you have a huge volume of data very quickly. So what we did next is to develop electronics that could actually handle reading those data and then being able to bring the data down to Earth with a sophisticated antenna. The last thing that we did was just the satellite around the camera. So truly the heart and the brain is the camera and the electronics that go behind. And it wasn't easy, but we're pleased now with the results. Okay, thank you. Yes. Yes, so that's also very interesting. When we had to develop to bring the camera to the ISS, that was especially difficult because if you bring anything inside the International Space Station, you have to be extremely careful that nothing can go wrong that will put in danger the lives of the astronauts. But our camera has glass. The glass can break. It has some mechanical parts. They cannot be pointy, so they will not hurt the astronauts. So in the end, has to be a very special type of glass that it is clear that will withstand the vibration of the launch and it will not break. In addition, you have to actually cover everything in a way that it will prevent for the astronauts to be hit by them and to have a wound, right? That was special for the International Space Station. Now, for the satellites that we're launching, they typically are materials that will resist the huge amount of radiation that is coming from the sun and from other places in the universe, and that we don't feel here on the Earth's surface because of the atmosphere that will actually absorb that. That means that you have a special type of aluminum, carbon fiber, and a special solar panels and batteries that can actually resist the conditions in the low Earth orbit. So they are similar to the materials that we use on Earth, but they have been adapted to being able to work in the very difficult environment of space. Thanks.
มีคำถามไหมครับ Anyone else has any questions? If not, let's move to the next section, which I think everyone is waiting for. So for the people who pre-register with NARED, so in the form we ask 2 questions about what is the object in the background of the flyer for this event, and also what would be the total mass of the object. No one got both of them right, but since some of you have at least guessed one or the other right, we picked the best 3 answers so far. So ครับก็ผู้โชคดีนะครับที่ตอบคำถามถูกอย่างน้อย1ข้อไม่ว่าจะด้านใดด้านหนึ่งนะครับก็เฉลยคือเป็น Galaxy Cluster นะครับ Abell 370มีมวลประมาณ10 กำลัง 15 ล้าน10 กำลัง 15 เท่าของมวลดวงอาทิตย์นะครับก็คือ100 คูณทิลเลียน so it's Abell 370 and the total mass is about like 100 trillion solar mass. So with that, also one of you guess, well, one of you said is iSIM camera, so that I will give you that one. So it's kind of like in the background, so both of them is fine. So the first lucky winner คุณพิมพ์ประภาใจคำครับครับผมลงมารับรางวัลได้เลยครับ
Thanks very much. Good luck.
The next lucky winner, I don't know whether I said this right. คุณพุทธิสประชาสิทธิศักดิ์ครับ So the last lucky winner who answered that the background is iSIM camera คุณเอมิลี่ปพิชยาโคคุส And last but not least, I myself have a souvenir for you. This is probably the one that started it all, started like event, and so Professor Rafael Guzmán received the advisor award from the Thai Research Council, and I just take a photo of the plate and email him, and he said that this one should be in person. So here we go.
Okay. Oh my God, actually. Yes. It really is very beautiful, actually. Thank you. Yes. We can just bring it here to the light. A little bit further. You can see it. Thank you.
And also from the generosity of the PR department, give us all the lucky winners, the souvenirs, and also for Professor Guzmán as well.
Well, I share with the winners. Thank you very much. Thank you, Pitapas, and please extend my thanks to the administration of NARIT. We really, really appreciate it. Well, I hope that I will be able to see you either here or if you come to Florida and Spain. If you have a chance, make sure that you can actually view the launch. It's a fantastic, fantastic experience. It really is. And let me know if you're in the area.
All right. So with that concludes, please everyone give a big round of applause for our PR department and also outreach department, also IT department, and our staff and engineers who presented today. Thank you so much.